In this video, we're going to focus on the Gabriel synthesis reaction mechanism. This reaction typically begins with a phthalimide, which is the structure that I'm currently drawing. This phthalimide, which is the name of the molecule, has a functional group called an imide. This functional group is basically the nitrogen version of an acid anhydride. It's a nitrogen between two carbonyl groups or two acyl groups. Now, there's two types of versions of the Gabriel synthesis reaction that you need to be aware of. Let's talk about the first version. The purpose of the Gabriel synthesis reaction is to produce primary amines. In the first step, we are going to add potassium hydroxide in water. In step 2, we're going to add an alkyl halide, in this case 1-bromobutane. And in step 3, we're going to add hydrazine, H2N, NH2. You can also write it as N2H4 if you want to. So what is the product of this reaction? Now, to find the product of the reaction is pretty straightforward. Look at the alkyl halide. All you need to do is replace the Br with an NH2, and that's going to be the amine that you want to create, or that will be created. Now, what about the side product? If you use hydrazine at the end, the side product will look like this. The name of this molecule is called Phthalimide Hydrazide. Initially, we had a 5-carbon ring or 5-atom ring, but now it's expanded to a 6-atom ring, which is more stable. 6-atom rings have less ring strain than 5-atom rings. So this is phthalimide hydrazide. That's the side product if you decide to use hydrazine. Now let's talk about the other version of the Gabriel synthesis reaction. Now in the first step, you're going to use a strong base. So we're going to keep that the same, potassium hydroxide. The second step is going to be the same. You can use any alkyl halide, but we're going to use a different alkyl halide. Let's use, in this case, 1-bromohexane. And in step 3, we're going to use water with hydrochloric acid in the presence of heat. And step 4, we're going to use potassium hydroxide. So what is the major product of this reaction? What type of amine will we get as our answer? Now keep in mind, all you need to do is replace the bromine atom with an NH2 group. And so this is going to be the amine that we're going to get. It's going to have 6 carbons and an NH2 group at the primary carbon. So the Gabriel synthesis reaction is very useful in making primary amines. That's the purpose of it. It converts an alkyl halide into a primary amine. Now what about the side product? So notice that we're not using hydrazine. So we're going to get a different side product if we use acid hydrolysis. The side product will still contain the benzene ring. But whenever you have a carboxylic acid derivative, if you mix it with H3O+, you're going to get a carboxylic acid. But because we have 2 carbonyl groups, it's going to cleave and produce 2 carboxylic acids. But notice that the final solution is basic. So the carboxylic acid will be in its deprotonated form. You can write it like this, or you can write it as COO-. Those two are exactly the same. So notice that the end result, the amine, used in both variations are the same. However, the side product changes. If you use acid hydrolysis, you're going to get 2 carboxylic acids. At the end of step 3, this is going to be protonated. and the amine will be protonated. This will be NH3. But at the end of step 4, everything is deprotonated since the solution is now basic instead of acidic. But let's go over the mechanism of the first example for it. So let's begin. What is the first step of the Gabriel synthesis reaction? That is the first version that we mentioned. We know the first step is the addition of a base. So what do you think the base is going to do? Because this nitrogen is next to two carbonyl groups, this hydrogen is relatively acidic, and so potassium hydroxide is strong enough to remove that hydrogen. And that's what it's going to do in the first step. So that's the purpose of adding a strong base, is to get rid of this hydrogen. Once we do that, we're going to get an intermediate that looks like this. The nitrogen is going to have 2 lone pairs, and so it's going to bear a negative charge. And the reason why the hydrogen is acidic is because the conjugate base is relatively stable. It's stabilized by 2 carbonyl groups. We can show one of the resonance structures by taking a lone pair and forming a double bond with it. So now the negative charge is not only present on the nitrogen atom, but is shared by the 2 oxygen atoms. So in this particular drawing, we can see that the oxygen on top now bears the negative charge in this particular resonance structure. And the nitrogen is neutral. So that's why this hydrogen is acidic. It's due to the resonance stabilization of the conjugate base. So what's going to happen in the next step? Once we add butyl bromide or 1-bromobutane, the nitrogen with the negative charge is going to attack the carbon that bears the bromine atom. The reason why it attacks that carbon is bromine is more electronegative than carbon, so the carbon bears a partial positive charge, bromine bears a partial negative charge. So the nitrogen is repelled by the bromine atom, so it approaches it from the back, but it's attracted to the partially positive carbon atom because opposites attract. And so this is an SN2 backside attack. And we're going to get this particular structure. The nitrogen atom now bears the butyl group. It no longer has 2 lone pairs, but it only has 1. And so that's the product after the second step. So for both versions of the Gabriel synthesis reaction, after the first 2 steps, you're going to end in this situation. The only thing that may differ is the number of carbon atoms attached to the nitrogen group. So for the second example that we use, since we use 1-bromohexane, this will have 6 carbons. But we're going to use this particular form for both examples. Now in step 3, for the first version, we're going to add hydrazine. For the second version, at this point, we would add water and HCl. So keep this point in mind because we're going to come back to it when using the second version. We're going to start here. But let's continue with the first version. And let's make some space first. Let's put this on top. So now we're going to add hydrazine, which I'm going to write it as H2N NH2. The nitrogen atom in hydrazine is a good nucleophile. It has a partial negative charge, and it's attracted to the carbon atom, which has a partial positive charge. So this nitrogen is going to attack this carbon from the back, causing the pi bond to break. And so we're going to get this particular structure. So this oxygen now has a negative charge. It has a single bond, and this carbon is attached to a nitrogen that has 2 hydrogens, which is attached to an NH2. And let's not forget the lone pair that is on this nitrogen, and it still has 4 carbons. Now the nitrogen with 4 bonds has a plus charge. So what do you think is going to happen? By the way, this step is reversible. This could form a double bond and expel the NH2 group, or the hydrazine group, taking it back to the left side. Now, instead of pushing this group out, what it can do is break this bond, because by doing that, it can obtain a 6-carbon ring instead of a 5-carbon ring, and so the driving force here is stability. So let's go ahead and take a lone pair and form a double bond, causing the bond between a carbon and a nitrogen to break, and those electrons will be used to form a double bond here, causing this pi bond to break. And let's not forget the bonds in the benzene ring. So right now we have this particular structure. So this nitrogen still has 2 protons, and we still have, let's see if I can put this over here. We still have the nitrogen, which is still attached to 4 carbons. The nitrogen still has a lone pair, but there's going to be a double bond here. Now the nitrogen with the plus charge has a relatively acidic hydrogen. The nitrogen with the lone pair is basic because the negative charge on the oxygen bears down on it. So this oxygen is going to form a double bond, causing the electrons in a pi bond to be more negatively charged, thus being attracted to the partially positive hydrogen. So it's going to act as a weak base, grab the hydrogen, causing this bond to break, pushing 2 electrons on that nitrogen. So what we now have is this structure. So this is back to a carbonyl group. This nitrogen now has a hydrogen attached to it, and it still has 4 carbons. We have another carbonyl group with a nitrogen and another NH2 group. This nitrogen has 1 hydrogen and a lone pair. Our goal is to put 2 hydrogens on this nitrogen, because we need it to leave as NH2. Right now it only has 1, so we got 1 more to go. Now before we carry on with the next step, let's make some space first. We have a lot of stuff on the board, and let's move this to the top. So what do you think is going to happen next? This carbon here has a partial positive charge, even though that partial positive charge is weakened by this lone pair. Now, which of these 2 nitrogens will attack it? If this one attacks, we're going to get the 5-carbon ring, but if this one attacks, we're going to get the 6-membered ring. I said 5-carbon ring, but really 5-membered ring. But if this one attacks, it's going to produce a more stable 6-membered ring. Another reason why that nitrogen is going to attack it as well is because the lone pair is localized. Therefore, those electrons are more reactive. This lone pair is delocalized by the carbonyl group, so it doesn't want to react because it's busy resonating with the carbonyl group. And so if we draw the resonance structure for that, this nitrogen has a positive formal charge, and so those electrons aren't available for nucleophilic attack. So therefore, this is the candidate that's going to attack this carbonyl group. And so now we have another 6-membered ring. Which looks like this. So this nitrogen now has a positive formal charge. And we still have the other nitrogen. So what do you think is going to happen in the next step? Now keep this in mind. This double bond could reform, expel in this group. So that step is reversible. But what we want to do is we want to get rid of this group because that's the amine that we're trying to acquire in this reaction. The only way to do it is to turn it into a better leaving group. Right now, it's a terrible leaving group. If the nitrogen leaves, it's going to have a negative charge and it's not going to be stable. So what we need to do is transfer a hydrogen from this nitrogen on to this nitrogen. How can we do that? How can we transfer a hydrogen from one region of the molecule to another? And the answer is the solvent. The solvent can transfer a hydrogen from one place to another. Now the solvent that we're going to use, we're going to keep it simple, is water. Depending on your particular reaction, the solvent might be an alcohol or something else. So you can always just change it. But we're going to use water. So water is going to grab a hydrogen from the nitrogen that has a positive charge because that hydrogen is a weak acid. It's relatively acidic. And then this bond is going to break. It's going to put a lone pair on that nitrogen. So these two nitrogens only have one hydrogen. So now we're going to use water to transfer the hydrogen that it just acquired. So once water grabs the hydrogen, now it's in the form of H3O+. So this nitrogen, being a weak base that it is going to take the hydrogen from H3O+. And so now we're going to have this structure. It's a lot of drawing in this particular video. So now this nitrogen has two hydrogens. So now it has a plus charge, which makes it a better leaving group than what it was before. So now this oxygen is going to form a double bond, breaking the carbon-nitrogen bond, expelling the NH2 group. So at this point, this is going to lead us to our final answer, which is Phthalimide Hydrazide. That's the side product. And also the product that we're trying to get, which is the primary amine attached to 4 carbon atoms. So that's the mechanism for the first version of the Gabriel synthesis reaction. Now what about the second version? Let's start from the point where we had the 4 carbons first attached to the nitrogen. Even though in the example that we used, it had 6 carbons, but let's keep it at 4. So starting from this example, what we're going to add is water and HCl. Now when you mix water and HCl, you're going to get an acid-base reaction. And this reaction is going to be driven towards the right. It's not reversible because HCl is a strong acid. And it's going to generate H3O plus and Cl minus. So when you put water and HCl together, you're going to get H3O plus, which if we want to, we can just write it like this. Now here's a question for you. Who is going to receive the acidic hydrogen? Is it the nitrogen or is it the oxygen of the carbonyl group? Think about it. To answer this question, let's draw the resonance structure of the molecule. The lone pair of the nitrogen is busy resonating with the carbonyl group, so it's not available to grab a hydrogen. If we draw the resonance form, Notice that the oxygen now bears the negative charge, and that the nitrogen bears a positive formal charge. Therefore, the nitrogen doesn't have a strong affinity for the partially positive hydrogen compared to the oxygen. So the oxygen is going to be the part that's going to be protonated in the molecule. So it's going to grab a hydrogen and it's going to expel water. So now we have an activated carbonyl system. So what is going to happen next? So what would you say? The next thing that's going to happen is water is going to behave as a nucleophile, and it's going to attack the carbonyl group. Now that this carbonyl group is activated by the H+, this carbon bears more partial positive charge, and then this pi bond is going to break. So now let's draw the structure that we now have. So this is now just a single bond attached to an OH. We still have the carbonyl group beneath that. And we also have water attached to that carbon. This oxygen now has a positive charge, and it's still a lone pair on the nitrogen. So now in the next step, another water molecule will act as a weak base, and it's going to take away a hydrogen atom. Giving us two hydroxyl groups. So we're going to have this structure. So now that the water molecule has acquired a hydrogen, it's now in the form of H3O+. Now, in order to break the ring, we need to activate the carbonyl group. And to activate it towards a reaction, we need to protonate it with a hydrogen. So what do you think is going to happen now? So this ring is going to break at this point. So this oxygen is going to use one of its lone pairs to form a double bond, and as that occurs, this bond is going to break. The two electrons in that bond will be used to form a double bond, and this pi bond is going to break. So as you can see, due to the positive charge, the electrons are going to flow from one side of the molecule towards the other side due to this positive charge. So that activated carbonyl group pulls the electrons toward itself, causing the ring to collapse and break apart. So now this is going to be a carbonyl group. We have an OH. This bond is no longer there. This is now a hydroxyl group next to a nitrogen. Now what I'm going to do at this point is flip this group with this group. So let's put the hydroxyl group on top and the carbonyl group towards the right. Now notice that this nitrogen with the lone pair is basic because the electrons of the hydroxyl group bear down on the double bond. This is going to form a double bond, causing this double bond to grab a hydrogen, producing a carboxylic acid on top. So this we can just leave it as COOH at this point. So we don't have to worry about that part of the molecule. Over here we have a carbonyl that is activated. We have a nitrogen with its 4 carbons, and now it has a hydrogen. So we need to add one more hydrogen to it before we can get rid of it from the structure. So what is our next step? What do you think is going to happen at this point? In order to get rid of this group, we need to protonate it with a hydrogen. We can't do it right now because these electrons are not localized. They're delocalized into the carbonyl group, so they're not available to grab a hydrogen. So for now, water is going to act as a nucleophile. It could act as a base, taking away this hydrogen, but that's not going to give us the product that we want. So we want it to act as a nucleophile. And so here is the OH2 group that we now have. It has one lone pair and a positive charge. Next, we're going to use the solvent to transfer hydrogen from the oxygen to the nitrogen. So another water molecule will be used to take away this hydrogen, giving us this structure. So we're going to have 2 hydroxyl groups. And now water has been converted to H3O+. So notice that this nitrogen can no longer resonate with a carbonyl group since it's not there. So now it can accept a proton from H3O+. So now we can convert it into a good leaving group. So it's going to grab a hydrogen, and we're going to have this structure. Now let's keep in mind this nitrogen has a positive formal charge. So now it's a better leaving group. So this oxygen is going to use its lone pair, form a double bond, kick out the nitrogen. And so what we now have is a protonated carboxylic acid. But we do have a primary amine. Now the solution is acidic, so it's not going to remain in this form. The amine can either grab a hydrogen from the solvent, or, since it's very close to the carboxylic acid, as soon as it's expelled, it can grab a hydrogen from it. So now, this is the answer after the third step. We haven't reached the fourth step yet, but after the third step, we can see that we have phthalic acid, which is fully protonated, and in addition to that, we have a protonated primary alkyl ammonium ion. So we have a nitrogen with 4 carbons and 3 hydrogens attached to it. So in step 4, we're going to add potassium hydroxide. The hydroxide ion will deprotonate the carboxylic acid. The carboxylic acid is a weak acid, and hydroxide will immediately get rid of these hydrogen atoms generated in water. So we're going to get this side product under basic conditions. So this is the deprotonated form of phthalic acid. And also, hydroxide will remove a hydrogen from the nitrogen atom, giving us our desired amine. So that's the end of this video. I know it's been a long one, but now you have the mechanism for both versions of the Gabriel synthesis reaction. So if you like this video, feel free to subscribe, and also check out my channel if you want to find more organic chemistry video tutorials. I also have videos on algebra, physics, general chemistry, pre-calc, trigonometry, and at the time of making this video, not geometry yet, but maybe in the future. So thanks for watching.